Welcome to week 1 for ISDA 609 Mathematical Modeling Techniques for Data Analytics. So before we get started on the formal chapters, we're going to review Chapter 0, which is Appendix D, for page Appendix 12. So please review all the contents in Appendix D and make sure you are comfortable with this math techniques and ask questions if you have any, either through Blackboard or email. So the major contents in Appendix D including the following: U substitution, integration by parts, rational functions, and partial fractions. Hopefully you are familiar with all these concepts from other courses. If not, review them and ask me questions if you have any. So for chapter 1, this chapter is called modeling change. I'll have a brief introduction followed by modeling change with difference equations, and explain to you how we can approximating change with difference equations, and what are the solutions to dynamic systems, and some of the formulations of systems of difference equations. Again, this is an example of flow of the modeling process. All the models starts from the real world data. It's a simplification of the real world data. And with the model, do some analysis, we can get some mathematical conclusions. And with the interpretation of these mathematical conclusions, we can have some predictions or explanations of the real world. And on the other hand, real world can be used as a verification of the predictions in turn of the math models. So this is a definition for proportional if two variables y and x are proportional if one is always a constant multiple of the other. That is to say, y equals to kx. So remember, this is how we write the proportion from relationship between y and x. So when we want to model a change, future value is equal to present value plus change. So if we want to model a change with difference equations, for example, a1 minus a0 is delta a0, a2 minus a1 is delta a1, so on and so forth, so that n's first difference is delta an equal to an plus 1 minus an. Some of these examples probably is not new to you, definition, but in general, they are really nice examples in the textbook at the end of the chapter. So I hope you can review this so that you have a deeper understanding of the concepts that we're talking. So here is just a graphical representation of the difference equations. So if at n period, this particular point is n, a, n, and n plus 1 period, it is n plus 1, a, n plus 1. But delta a, n is just a difference between those values, a, n plus 1 minus a, n. So this is an example when we apply for a mortgage for a home, we could well model the problem as bn plus 1 equal to bn plus 0.01 bn minus this constant, b0 starting from the initial loan. So modeling change with difference equations. A sequence is a function whose domain is a set of all non-negative integers and whose range is a subset of the real numbers. So a dynamical system is a relationship among terms in a sequence. A new numerical solution is a table of values satisfying the dynamical system. So this is not new. I don't think it's new for everybody. So let's say uh, if we can somehow to approximate the change, assume that this discontinuous versus discrete versus continuous change. For example, if it's discrete, so that uh, we can in this example we can approximate the change by 0.15 times Pn, the value at the previous 0.5 times the value of previous period. Let's look at this example. If it's continuous change, we can model as a straight line. Later we would learn this is a linear regression. Uh, yeah, actually in this case uh, it is not a linear regression. It's actually a nonlinear. It's actually a nonlinear model here using data n. I mean to model the data xn. It could take this form. It's a linear model, I believe. Yeah, it is. So and then we can see that in the example in the text, it essentially says these are the predictions from mass modeling, and this is the real observations. As you can see, in some of the locations it fits really well. In some other locations it doesn't fit well. But later on we could learn how can we measure the fit, meaning how good the model is. So the solution for a dynamical system, we could look for a pattern and conjecture, test the conjecture and conclusion. The conjecture itself could be a mass modeling process. Now here it says linear dynamic system, an plus 1 equal to r times an. R is any non-zero constant, so that ak is r powered by k times a0. I believe you have learned this in high school and hopefully in your undergraduate studies as well. And the linear dynamic system, so essentially it is trying to find this number a that could satisfy this dynamical system to find so that you can find a solution for this particular linear dynamic system. The solution is AK is in this form. So for nonlinear system, so an plus 1 is nonlinear in terms of an. As I mentioned here, from page 37 to page 52 are very good examples of system of difference equations. Remember that all these examples will be covered later on in the course as well. Meaning, it's better that you can understand these examples understand what it is and how we are using this particular math modeling technique to solve the problem. And later on, we could be using some other techniques to solve the same problems. Again, make sure you understand all these examples and pay attention to sensitivity of initial conditions and ask me questions if you have any. This is a chapter 1 homework. Please make sure that you hand in your homework by the end of the week before 12 o'clock on Monday every week. Okay, enjoy the reading and ask me questions if you have any.